So let me tell you a little bit of my background. I started as a mechanical engineer long time ago, and decided kind of late, actually it was New Year's Day my senior year, I decided I had job offers. I decided I wanted to go to a graduate school and do a PhD, and considered where to go. Ended up, as you heard, going to Yale, getting a PhD in applied physics, and studied the use of lasers to understand turbulent reacting flow. So a little bit of combustion, a little bit of quantum physics, a lot of hands-on electronics and building lasers, and just a lot of different kinds of things, and really made me exposed to a very, very broad set of detailed physical analysis, comparison. There were some questions about comparison with modeling. That was the early days of computational fluid dynamics. We were trying to validate some of those codes. Back then, everybody was getting the wrong answers. And so we were developing some of these spectroscopic-based measurements and high-speed digital imaging back when, now we all have cameras in our phones, right? Back when I had to custom build the chip, build the camera, build a set of boards to stick into a computer to digitize the information come from the camera, and write assembler code to get the pictures into the computer, and then write the computer graphics algorithms to draw the videos. I know I don't look that old, but technology's moved pretty quickly, and so to do that, I learned a little bit about a lot of different topics, and that sort of gave me a taste to want to work in a lot of different areas. So when I graduated with my doctorate, I went to work for United Technologies Research Center, a company you just saw the video describing the products, which was really, really neat. It was a small research laboratory with a little over 1,000 people. It's a lot smaller today. About 60% was advanced degrees, masters, and PhDs, and I got to go play in the lab. It was a blast, and was studying combustion for Pratt & Whitney, actually. Just to give you a perspective, that was almost exactly 25 years ago. Okay, and at the time, was having a great experience, publishing a lot of papers, probably publishing about 10 papers a year, doing a lot of very cool fundamental research, great, lots of budget to go play with lots of really neat toys. And after a couple of years, I was running that group and discovered that jet engine, we talked about efficiencies in jet engines before, the combustion process is probably 99% plus efficient. And emissions at the time weren't a real driver. And so there wasn't a lot I was going to do. So I started working with Carrier. And you heard me say earlier, 60% of the energy is used in buildings. Probably about 46, 48% of that is actually in the heating and cooling of those buildings. And 35 in some more modern societies. And the big opportunity was in the heating and cooling. So started working on that and discovered this is a systems problem, right? You have to look at it as a building as a whole. And started working on alternate thermodynamic cycles. So rather than just trying to perfect the compressor or the heat exchangers in the heating and ventilation system, started looking at it in terms of indoor air quality, right? How do you manage the quality and the comfort of the occupants? Not how do you make it hot and cold. It's a very systems engineering perspective, right? You're asking a different set of questions. That different set of questions leads you to optimizing the system at a fundamentally different level, which leads to these architectural differences that you can achieve. And from that led to, well, if I'm using an electrical generating system, such as a fuel cell, and I use that waste heat, I can take the fuel cell from 40% efficiency to 86% efficiency because I'm using some of that waste heat to either heat the building or in a hospital to preheat the laundry, right, the water used in the laundry system and so on. And by doing that, I become more of a systems level optimization at the building. I'm just going to give you another example that you won't see here in this talk. the new building at 4 World Trade Center, we make the comfort system, the environmental control system, the security system, and the fire system, and the elevators in the building. So you walk in the building in the morning, and you scan your badge. Instead of going to an elevator and pushing a button and waiting, there's a bank of elevators, and it has queuing theory. And it tells you which elevator to get on. So it's optimizing the shortest wait time for you, because it knows chances are first thing in the morning, chances are you're going to your office, right, or your department. And so at the same time, it wasn't managing the heating and cooling of your office. It could shut it down because it knew you weren't in the building. And so it says, I've got 2 minutes to get this office comfortable enough for that person to be there. So it suddenly turns on the heat full blast or the air conditioning full blast to get that office comfortable, because it knows that there's a high probability you go into your office. And it turns out when you start to build on the infrastructure and you think about optimizing at the system level, you end up with much better efficient solutions. And it turns out to make it really hot or really cold quickly, that usually means a less efficient system, right? Because I need bigger heaters and bigger air handlers, but by optimizing the whole system, that I can shut down the spaces that aren't in use when I know the person's left the building, then you can actually, maybe I oversize one part of the system, but the entire system at the building level, I'm saving energy. Okay? That's a really good example of systems modeling that could lead to systems optimization. Now, UTC was really built by a bunch of engineers. And I'm going to tell you their stories and then fast forward you to some of the products we're doing today to show that spirit innovation that our engineers are doing is continuing. Just to finish my story, just to bridge you to the present, I spent 14 years at the Corporate Research Center. I led the fuel cell program. I led Hamilton Sundstrand. I led the Sikorsky Advanced Technology program. I joined Pratt & Whitney about 11 years ago, a little less than 11 years ago, and have been with Pratt & Whitney in different capacities since then. However, I maintain some levels of technology responsibility across the corporation today, working with our Chief Technical Officer of the corporation. So UTC was really built on this notion of dream, dare, and deliver. And it's a combination of focus on responsibility and that lets us build on this, our responsibility to those founding fathers, that has let us continue to build on this and think like this when we think about the society and the infrastructure of society that we provide today. Our founders used these principles to define modern society. A little over a century ago, an engineer named Willis Carrier worked in New York City for a printing press. And the problem was, and you've probably seen this in your own printers, the problem was that when the heat temperature changed, the inkjets didn't align. And so the printing process, rather than making the true colors, the colors were coming out differently. And so what he did was he came up with a system that allowed for the temperature control in the environment in this printing press, so that on the hot summer months that they were able to continue to operate this printing press. In 1911, he was or shortly before 1911, he was sitting at an elevated subway station, and he was pondering the question of humidity versus temperature. It was a foggy night, and the train went by, and all of a sudden he had an epiphany of understanding the relationship between absolute humidity and relative humidity as a function of temperature. Has anybody here taken thermodynamics and dealt with the psychometric formula? right? He published that with the American Society of Mechanical Engineers in 1911, right? So he's the guy, Willis Carrier, that this company was founded by. Today, it's the world's largest producer of heating, ventilation, air conditioning systems. The picture here shows what they used to do in train cars before they had air conditioning. They would actually shovel thousands of pounds of ice underneath the trains, as you can see, and they'd blow air over it to cool the passengers. Air conditioning, once it was available, was added to buses and progressed over the years. Now, when you think about today, as we feed the almost 7 billion people on our planet, one of the critical things is preserving the cold chain on the food to keep the food fresh and safe from the point of generation to the point of consumption. Today, most of those refrigerator containers, those refrigeration units, are produced by Carrier. And we were the first to eliminate ozone-depleting substances, or the CFCs. In fact, when the Montreal protocols were put in place, we got rid of the CFCs about 8 or 10 years before the Montreal Protocol went into place, banning the production of those chlorofluorocarbons, even though initially the thermodynamic efficiency was lower, because we felt it was the right thing to do. Today's refrigeration systems are based on hydrofluorocarbons, but those hydrofluorocarbons can still still have a global warming potential, right? Global warming potential is usually measured in units of CO2, right? So water, for example, is a global warming gas, and it's very much higher than CO2 in its water vapor and its ability to trap heat in the environment. Today, with this unit, which we've just introduced in Asia and in Europe, is a refrigeration unit that uses CO2 itself as the refrigerant at very, very high pressure. So if you think about it, we've gone from these chlorofluorocarbons to the hydrofluorocarbons, but they still had a global warming potential in the, depending on which one, somewhere between 20s to the 40s times CO2. And we're using CO2 itself, but rather than creating chemicals, we're taking the CO2 out of the environment and we're squeezing it into these systems, essentially sequestering it out of circulation, out of the environment, in compressed state into these. So by doing this, not only is it a more thermodynamically efficient system, about 28% lower global warming potential, but combination of the CO2 you've taken out of the environment and the efficiency of the system compared to other energy-consuming devices to do the same function. So that's a great example of systems engineering today. In 1850, the tallest buildings here in New York City were 6 stories tall. In 1853, the urban landscape was constrained by that. And so Alicia Graves Otis in 1853 came up with an idea. They had these dumbwaiters to carry things up and down, but they weren't safe because when the cable broke, the elevator would fall, bad things would happen, right? And so what he conceived was not making the cable safer, but a safety brake. Again, he looked at optimizing the system as a whole. And the safety brake worked that when the cable tension was released, it let the car itself latch onto the rails. Now, he introduced this in 1853, and nobody paid attention. So he came here to New York, and he worked with, actually, I recently discovered this, P.T. Barnum. And P.T. Barnum was a great showman. And he staged this event. He called this big press conference. And he goes up to the top of a building. All these reporters are there. You know, this is 1853, right, with their flash cameras and whatnot. And he gets up on the roof of the elevator, standing on the top of the elevator, you know, next to the cable, with a great big cable cutters. And he cuts the cable. He had a dream. He dared. That's seriously daring. And it fell a few inches and stopped. And the result of that are the landscape of the cities that we have today. This is actually a model that shows the safety brake up at the top. And now, this is the Burj Khalifa, currently the tallest building in the world. I forget exactly how tall it is. Is it 900 meters, I think? It's just shy of a kilometer tall. And there are numerous buildings under construction and design right now that are going to be even taller than this. Our Gen 2 elevator is used in this, where rather than using a cable at all, it uses a coated steel belt. See, the problem is when you've got a cable, you've got this huge weight of the cable, and you wrap it on this big, big spool. And you need a big spool. And the reason you partly need the big spool is to get the traction. But when you get a cable, it stacks up, and it takes up a huge amount of space. You couldn't make a building like this because the cables for the elevator on the spools would be too big. And so what we re-engineered was making the cable, instead of round, we made it flat. And it's just a series of coated steel cables in a rubber belt. And it rolls up flat. This is an example of our NCE, or Next Step escalator. And it's even more energy efficient. It actually senses whether there are people on it and how many people are on it. And it's got a variable controller, so it turns down the energy utilization when people aren't using it or when there are fewer people using it. So it senses its load. It also has LED lighting to be even more efficient. Shows a way how we continue to dream, dare, and deliver. After World War I, Captain Frederick Rensselaer left the Army, and at the time, all of the aircraft engines that were used in World War I were water-cooled. And this led to a huge reliability and maintenance problem. But if you think about it, it was another system that was particularly vulnerable. Because if you lost the coolant, the water would run out, and then the engine would overheat, and the airplane would fall down. Furthermore, it required a great deal more weight on the engine for the weight of the water, the cooling system, and the jacketing of the water in passages inside the metal. And so in 1925, Frederick Rensselaer formed our company, Pratt & Whitney, and they produced the air-cooled engine. And the way this engine works, and I don't know if you can see it, but each piston is actually standing out and surrounded by its own heat exchanger. It might be more visible in the prior picture. You can see this, each cylinder is its own heat exchanger around it. And so essentially it increased the thrust to weight by about a factor of 2 to 2.5 available. And in World War II, we made almost 500,000 of these engines. It is the engine that really played the dominant role for us and our allies in World War II. Today, we've introduced a new engine, which I mentioned earlier, we certified last week. It's the Pure Power engine. And remember I told you earlier that by embracing about a 2% efficiency change in the fan, a 2% in the gearbox, and 2% in the back of the engine, we ended up getting about a 16% improvement in the overall efficiency of the fuel burn of the engine. It also turns out that it's about 75% quieter. So now that I just spent the prior hour teaching you how jet engines work, right? There's the inner spool, and then there's the outer spool, right? Remember we talked about how that low turbine in the back spins the fan that actually makes the airplane go through the air. That's where most of the propulsion comes from. Well, it turns out the faster you spin that low turbine, the more efficient it is. But the slower you spin the fan, the more efficient it is. And if they're both on the same shaft, then you can't co-optimize both. And so using some of the tools that I described to you in the first part of the lecture, we introduced a gearbox as a technology to slow down the fan. And we came up with the optimal gear ratio that lets us slow down the fan but spin the turbine at its optimal speed. And it has that gearbox by about 3.5 to 1 ratio. And by so doing that, it turns out most of the noise in the jet engine is actually the speed of the tip of the fan is supersonic. And that's where most of the noise is generated. So by slowing it down, it's 75% quieter. What does that mean? 16% fuel burn, I think I mentioned, is about $1.5 million per airplane per year. Put that in terms of CO2, that's 3,000 tons of CO2 not burned by that airplane in a given year. Now, let's put that in more generic terms. Consider a tree in the forest. That tree, when the sun is shining, sucks CO2 out of the atmosphere and essentially sequesters it. 3,000 tons of CO2 is the equivalent of 700,000 trees. 700,000 trees per airplane per year. Now, I mentioned we just certified the first of these engines last week. We've actually sold over 3,500 of these engines. These are for two engine aircraft. You can do the math. When I go to Washington, I spend a lot of time in Washington. The congressional delegates always ask me to put that in terms of districts, right? How many acres of trees is that in terms of votes? But that's how Washington works. But I mean that is a profound difference. In World War I, people used to fly airships a lot, right? And this was a B-class blimp. And similar to today, in 1917, there was an engine that went into these blimps. It was a 12-cylinder engine, V12 engine. And that was also developed by another part that became Pratt & Whitney. Today, we're making the engine on the F-35 Lightning II. As I mentioned earlier, this airplane flies at about Mach 1.6, almost Mach 2, and can land vertically on the deck of a ship. Don't even need an aircraft carrier, right? Just hovers and lands. There are 3 variants of this aircraft, one for each of the branches of the Marines, the Navy, and the Air Force. And there are partner companies, core partner countries, and other partner countries. About 12 countries are NATO partners, as well as Israel and Australia and others are partners, and Japan have already purchased these aircraft as well. We've delivered these to the U.S. Air Force, to the Marines, to the Navy, and to our British allies thus far. About 50 airplanes have been delivered. This engine, single engine aircraft, produces 43,000 pounds of thrust. When it's hovering like this, that lift fan I showed you before is going through there's a clutch in there and a gearbox with about 28,000 pounds, 28,000 horsepower going through that. And that's the kind of engineering, systems engineering that we're doing today. Right? Optimizing not how do I make my ship, my aircraft carrier better, but can I make my Mach 2 capable airplanes land on any ship? Okay? In 1490, Leonardo da Vinci came up with this concept for a helical screw helicopter. But for almost 450 years, the notion of vertical flight was not realized. In 1931, Igor Sikorsky invented the helicopter. And with that, he, as I said earlier, he did this because he felt he could use this and society could use this to save lives. Now, this is actually him flying the first one. You can see with his hat. We actually have the office in Stratford, Connecticut. We preserved his office. It's still there. And that hat is sitting there behind the desk. Same hat. I've had occasion to speak alongside Sergei Sikorsky, Igor's son. And he tells the story about the first time when they actually took this picture. And they rolled out the airplane. And his dad, Igor, was pushing on the landing gear on one side. And he was a little kid at the time. And he's pushing along with this guy, and he looks up, and it's Charles Lindbergh. So they were pushing this out, along with Charles Lindbergh. They were pushing the helicopter out for the first flight. And he flew this thing himself. He dreamed, he dared, and he delivered. And as I said, he did this because he knew it was going to save lives. Today, we're taking this to the next level. One of the constraints on a helicopter is, in a helicopter, it's kind of neat. Since you're all engineers, I can't help myself but just go a little bit technical depth. When the blade goes around on a typical helicopter, we'll go back one. When the blades go around on a typical helicopter, the angle of attack on the blades is actually changing so that the lift is the same. When you're in forward flight, the blades that are going backwards actually pitch upwards so that you get the same lift. Otherwise, the helicopter would vibrate itself, tipping as it went. And so as the blade goes around, it actually has to change its angle of attack. And at some point, the limit, the fundamental physical limit to how fast you can fly in a helicopter is that the backward going blade at some point is not going to generate lift because the tip of that blade is going to be going backwards right too fast. It's never going to generate lift. And airfoils don't fly real well backwards. So what we did, and this was about a little over a year ago, we made this aircraft. This is the S-97 Raider. The demonstrator was the X-92, and the X-2 demonstrator. And basically, there are counter-rotating rotors on the top, and then there's a little pusher prop here. And with this, we broke the world speed record in a helicopter was 220 knots, nautical miles per hour. And with this, we broke the world speed record of 253 knots. And this is under consideration now for future light attack aircraft by the Army. In 1927, Charles Lindbergh made his historic flight from New York to Paris. And I'm proud to say that the logo on here is the same logo as the Hamilton Standard propeller was on that airplane. Air travel continued to grow since then, and as you could see, maybe it's a little more comfortable today, but if you're sitting in a middle seat, it's not a whole lot more comfortable. But perhaps with some of the hiccups on the Boeing 787, today that's what it looks like. I had a chance, I got the VIP tour at Boeing out in Seattle, and we got to climb over half-built 787s. And it really looks like that inside. It's really pretty cool. We make most of the subsystems on this airplane. All the actuation systems, all the electrical systems, all the, no, we don't make those lithium-ion batteries. Secondary and emergency power systems, landing gear, brakes, pretty much all the systems that make that airplane go. And today, the auxiliary power unit, which is out back in the tail there, is also, that's now part of Pratt & Whitney. So it's all part of the same system and family. Now, I can tell you that I personally am spending my time every week working together with my brothers and sisters at United Technologies Aerospace Systems, because they make the nacelle around the engine. I did it again. They make the nacelle that goes around the engine while we make the engine. They make the electrical power distribution system and the electrical generators that run off of our engine, that takes electricity from our engine. And so I know that while we talked earlier about the ultimate thermodynamic efficiency available under the Rankine cycle, under the Brayton cycle for the engine, and under the Rankine cycle for the cooling systems on these aircraft, which use a vapor cycle cooling system, and that there's a way to not optimize just the engine, and not optimize just on the cooling system, and not optimize just on the electrical power system, but to optimize the aircraft as a whole. All right? So we're building the models that let us parametrically simulate the airplane that includes all these other subsystems and lets us morph and consider technologies that maybe doesn't make the engine the most efficient, or maybe doesn't make the electrical system most efficient, but that on the long run will make the airplane most efficient. And we started this at the beginning of the year, and here we are at the very end of February, and we've already found ways to make the aircraft several % more efficient in terms of fuel burn by that co-optimization. And to be able to do that and get it into the fleet within this decade, if the right market opportunities persist. So those are very real. Again, a % savings in fuel burn represents a tremendous amount of fuel, like of order 500 million gallons of fuel on an annual basis for the airlines. Those are real opportunities. Today, we have over 20,000 engineers and scientists across United Technologies Corporation. We have about 210,000 employees, and about 20,000 of them are engineers. And our focus is to make products that make the world cleaner, safer, and more comfortable. Our commitment to innovation and technology is evident. We spend somewhere between $3.8 and $4 billion a year in engineering across the divisions of United Technologies. For over 80 years, United Technologies Corporation has remained true to the commitment to a place where the world's best scientists can create technology options that deliver our company to be the ability to contribute the infrastructure of society. And so I think as a systems engineer, it's a really cool place to work because you get to work on the things that really are defining what society is going to be in the future. And we talked a little bit about modeling. You got to combine the technical expertise. I talked earlier, you got to be good at engineering the system. You got to get the fundamentals. You got to really understand the technical details in depth to be able to provide those detailed models and then combine them with your experiences and look at the opportunities from the macroscopic perspective. One of my mentors sent me a paper once. It was one of these leadership Harvard Business Review articles, but it talked about systems engineering from a Harvard Business Review perspective. But it had in there a term that I found really interesting. It talked about the ability to dance on the dance floor and enjoy the view from the balcony. To dance on the dance floor and enjoy the view from the balcony. Our engineers, as I said, we have about 200,000 people in the company. We're in about 70 countries, and we engineer our products from start to finish, from cradle to grave. We worry about what happens to them and how do we recycle. And it's really important that we look at the people and the science and the technology that go into our products. I'll show one more video. We're getting to the end.
A lot of the products that are out there, people don't really think about.
You see airplanes flying, but you don't see the hundreds of thousands of components there are to craft fly.
It is very easy to take what we do for granted because nobody sees what we do.
A lot of people don't give a lot of thought as to what an elevator really is. I push a button and there's a machine that sends it to me. It's something you can take for granted. We want you to take it for granted.
It's very easy to think of technological development as zeros and ones, but everything that is made is touched and designed and agonized over by people.
Despite all the advanced technology and our products, we know there are still challenges to be solved in the world. I look forward to a day when there's sufficient energy and it's available to all. I look forward to a day when we can look at the grand challenges and build cities of the future that are environmentally sustainable, comfortable, and livable. But a significant portion of humankind does not live in cities like that. A significant portion of humankind doesn't get to travel. Something like only 15% of the world's population has ever enjoyed air travel. 15%. And many people don't have access to clean water, to toilet facilities, or even healthy food. And so we as systems engineers, in some sense, share responsibility. It's up to us to think about these grand challenges and not solve the engineering problem explicitly in the little corner of the little subsystem, but think about it in a global sense. Think about it in a broad sense. Think about it in the context of how that product is going to operate in society and make a difference to the people that surround us, to make a difference to the emerging portions of the world, to make a difference to the children who grow up without access to clean water to drink. That's the opportunity that we have. And yes, I recognize that some of that is also tied up in the military products that allow us to sustain our freedom and enjoy the freedom that we have. And those two represent opportunities for us. Opportunities for us to use our engineering talent. It's not just something that we can do, it's something that all of you must do. And the way to do that is you start with a dream. You take on a dare. You know, you may not have to go up on that elevator and cut the cable or be the first to fly in the next in the anti-grav machine that you come up with. I don't know. But take a dare. Sometimes it's a personal dare. Sometimes it's taking a step out of your comfort zone. As long as you know you're technically accurate and correct and right, then you should feel empowered to do that. And as engineers, you know, you're being, at a school like Columbia, you're being given the tools necessary and the skills necessary to know when you've calculated something and you know you got the answer and you can know it's right, know it makes good engineering, physical sense to you, right? Build upon that. Let it spur your confidence and think about how you use that to really make a difference for the people around you, for the companies you end up working for, the communities where you volunteer, the nation that you live in, and society as a whole.